So the second step here is making use of this double bond that we created. So the double bond between the two carbons here. We can actually undergo a hydration reaction. So remember, in hydration reactions we're adding water. So adding water, we actually split that water into two. So one group that we're going to add is going to be the OH, and the second group is the hydrogen. So by removing one of these double bonds between the carbon, there's now two new bonding positions, and you can see what attaches to those bonding positions. So it's the two halves of the water molecule. So one of the carbons will accept a hydrogen and one will accept the OH. So this creates our alcohol group. So that's what we've done in this reaction. We've converted an alkene in these two carbons to the alcohol. So now that we've actually added these hydrogens on, we can actually facilitate another oxidation reaction. And this time the oxidation reaction is actually facilitated by the NAD plus coenzyme. So in step 1 we use FAD, but in step 3 we use the NAD. So this reaction is very much the same as in step 1. We have the oxidation of the reactant, and that is being oxidized by our coenzyme, which is reduced to the electron and hydrogen rich form, which is NADH. So the hydrogens that are removed from the acyl variant, which now contains the hydroxyl group, are shown here in the orangey color. So we take those hydrogens off, and then we're actually able to put these onto the NAD+. So without the extra hydrogens, the carbon will now need to form an extra bond to the oxygen, and that's what allows it to form the COO group. So because the COO group is actually attached to carbons on either side, we actually call this a ketone. So we've gone through all these steps 1 to 3, to convert two carbons that were just attached to two hydrogens, and now we've got a carbon that is attached to an oxygen via a double bond. So we've created this ketone group. So the last thing to do is actually to cut our reactant that we've created here. So we're going to remove a acetyl-CoA from the acyl group, which contains the additional carbonyl group that we just created. So in step 3, we've created this carbonyl group, and we're now going to cleave this at this point. So you can see down the bottom here where this actually happens. So we've got a cleavage point represented by this squiggly line. So cleavage meaning break. So you break these two pieces in half, and this is facilitated by a thiolase. So we have two things happening here. We have the release of the green part, which is actually acetyl-CoA. So we've got the acetyl group on the left hand side, and on the right hand side we've got our CoA. We also have an additional CoA being added in, so we can now connect to the remaining part of the acyl chain. So essentially all we've done is removed these two carbons, which are now a part of the acetyl-CoA that's been removed, and we've now regenerated our acyl-CoA with two less carbons. So basically we went through this whole process to create acetyl-CoA, and by doing this we were actually able to take two carbons off the acyl-CoA. So this is what we're doing in beta oxidation. We're shortening our acyl chain by two carbons every time we do our beta oxidation cycle, and by doing this we're actually able to produce an acetyl-CoA. So we can see the summary of this in this box here. So every beta oxidation cycle is able to make one acetyl-CoA, and by doing this we actually shorten our fatty acid or acyl-CoA by 2 less carbons. And importantly, the process doesn't actually finish there. We can actually use that acyl-CoA that we've created in the product here to re-enter beta oxidation, and we just go through the same process again to make another acetyl-CoA, and then your acyl chain will be another 2 carbons shorter, so we can just keep going until there's no carbons left. At that point you would have completely broken down the acyl-CoA into individual units of acetyl-CoA. So that's what we see depicted in this process of beta oxidation. So here we're talking about beta oxidation of a saturated fatty acid that contains 18 carbons. So the first step is to undergo the 4 steps of the beta oxidation, composed of the 2 redox reactions, steps 1 and 3, and the hydration to make it an alcohol in step 3, and then the thiolysis in the last step to separate the acetyl-CoA and the new acyl-CoA. So after we've generated our new acyl group, you'll notice now that it actually has 16 carbons, whereas the one up top here actually has 18 carbons. So we've shortened our chain by 2 carbons. So every time we do the beta oxidation spiral, we're actually shortening our acyl chain by 2 carbons at a time. So if we do it again, we go from 16 to 14 and we release another CoA. Then the next time we get to 12, etc., until we're all the way down to a 4 carbon compound. And then when we have a 4 carbon compound, we'll actually be releasing 2 acetyl-CoAs instead of just 1, because the acyl-CoA that you actually make only contains 2 carbons, and that actually makes it acetyl-CoA. So the simple way of remembering that is basically the last step, the last spiral of beta oxidation doesn't give you 1 acetyl-CoA, it just gives you 2, and that's all you're left with. So you can see how, starting with 18 carbons within our acyl-CoA, we're able to generate lots and lots of acetyl-CoA. So we'll have a couple of rules that tell us how many acetyl-CoA we're actually able to get out of beta oxidation, and we base this on how many carbons the original fatty acid actually contains. But not all of our fatty acids are saturated. So there's a few extra reactions we would need to do if our fatty acids are unsaturated. So we do actually need these 2 additional enzymes when we have unsaturated fatty acids. So our double carbon-carbon bond within our unsaturated fatty acids are naturally in this cis isomer form. So this is why we have cis unsaturated fatty acids, not trans. So trans are quite rare. We saw this in our lipids lecture. So the first thing we have to do is we have to hydrate this double carbon-carbon bond. So we turn the cis isomer into a version which instead has attachment of the OH group. So we saw basically how this reaction would work within this step. So you're just taking a double bond and converting it into an alcohol group. So this is the first thing you need to do if you're using an unsaturated fatty acid. We then use another enzyme to actually change the format of this product, which is we originally produced the L-hydroxyl acyl-CoA. We originally produced the D version, so it's the right-handed version, and we need to actually change it into the left-handed version. So we're using a epimerase, which is actually changing the stereoisomer form from D to L. So we can see the representation of what's happening in this reaction down here. So we have the OH that was down the bottom is now at the top. So it's now the left-handed version. And once we have the L version, the L-hydroxy acyl-CoA, we can actually enter step 3 of beta oxidation to convert it to the ketone. So we can convert our L-hydroxy acyl-CoA into the ketone, which is then used to cleave off an acetyl-CoA in the last step. So basically, by doing these two reactions within the unsaturated fatty acid, we're actually able to enter step number 3. So this compound will be used at the start of step 3. So we'll undergo a dehydrogenation reaction to convert this into a ketone. So we can connect to the other steps that we were having a look at when we were using the saturated fatty acids. However, in some unsaturated fatty acids, the carbon-carbon double bond is actually on an odd carbon instead of an even carbon. So our enzymes can only deal with the carbon-carbon double bond when it's on an even carbon. So we actually have to change the position of this carbon-carbon bond by doing a cis-trans switch. So we turn, instead of it being the 3,4 double bond, which is cis, we can actually switch it to a 2,3 double bond, which is now trans. So the cis has both of the hydrogens on the same side, whereas the hydrogens in our trans configuration are now on opposite sides. So notice that the double bond starts with an even number here, so it's 2 instead of a 3. So now we're actually able to use this product in our beta oxidation process. So this can be the alkene, which is then able to turn into the secondary alcohol and then the ketone in the same way I showed you with the saturated fatty acids. Alright, so it's key that when we're doing beta oxidation pathway that the fatty acids that we're using have an even number of carbons. So that's what these fatty acids have. You don't find them with an odd number of carbons. So that's fine. And because they always have an even number of carbons, this allows us to predict how many times we're actually going to do the cycle and how many acetyl-CoA molecules we're going to get out of the cycle. So the number of acetyl-CoA molecules that you get out of one fatty acid is actually half the number of carbon atoms. So for example, if you have a fatty acid that contains 18 carbons, then if you halve that, divided by 2, you get 9, and that tells us that you're actually going to get 9 acetyl-CoA out of a fatty acid with 18 carbons. So just halve the number of carbons and you get the number of acetyl-CoA that you're going to get. And to work out how many beta oxidation cycles you actually need to do, you can do the same rule. So you do 18 divided by 2, and then the next thing is you just have to minus 1, because it is 1, the number of turns that you need to break it down of the beta oxidation spiral is 1 less than the number of acetyl-CoA, because the last turn actually produces 2 acetyl-CoA. So it's the same rule, except you just minus 1. So now we've got 8 turns required. So we just need to do 8 turns or 8 spirals to fully break down our 18 carbon fatty acid. So we can see another example here. If we have a 16 carbon fatty acid, then you're going to get 8 carbons, you're going to get 8 acetyl-CoA. So that's half the number of carbons, and it's going to require 7 turns. So it's half minus 1 from the carbons. Alright, so we did all this beta oxidation to get two things. We produced these electron-rich coenzymes, and they are the FADH2 and NADH. So remember, every time we do the beta oxidation cycle, we're producing one of these each. So the FADH2 is produced in step 1 and the NADH is produced in step 3. So now that we know we're getting one of these for each time we do the cycle, if you have a type of fatty acid, then you can actually work out how much ATP you're going to be able to generate out of it. So based on how efficient the coenzymes are at deriving ATP once they get to the electron transport chain, we can say that FADH2 will give us 1.5 ATP, whereas NADH will actually give us 2.5 ATP. So for using the rules that we've already had a look at, if the stearic acid has 18 carbons, then that tells us that we're going to get 9 acetyl-CoA from it. And we know from an earlier session that when we have an acetyl-CoA, each of these acetyl-CoA is able to generate 10 ATP by going through the citric acid cycle, electron transport chain, and oxidative phosphorylation. So you can look back at an earlier session if you want to get some more detail on that. So we've done 8 turns of the beta oxidation cycle to generate our 9 acetyl-CoA. So we get 8 of our FADH2 and 8 NADH, because we get one of each every time we do the cycle. So then it's just a simple calculation, times in the number of acetyl-CoA by 10 ATP and the number of the coenzymes by either 1.5 or 2.5, depending what they are. So if we add that all up, we get to 122 ATP. However, we actually needed 2 ATP to activate the fatty acid initially, so we actually have to minus 2. So the net ATP production from our stearic acid, which contained 18 carbons, was actually 120 ATP. So we saw in the earlier session that we actually were able to generate 30 ATP from a single glucose. So if you want more of an explanation for how this occurred, just look back at that lecture. Just using this number to compare the efficiency of the glucose metabolism to the fatty acid metabolism. So we can see here, if we have one glucose, from that glucose you get 30 ATP, whereas from our stearic acid we're actually getting 120 ATP. It's not quite as simple as that though, because the glucose has only a third as many carbons. So let's try and work out how many ATP we're getting from each of these sources per carbon. So if we times our glucose by 3, now we've got it to the equivalent of 1 stearic acid, because there's 18 carbons in 3 glucose. So we also times the number of ATP by 3, so we've now got 90 ATP. So from 18 carbons of glucose we get 90 ATP, whereas from 18 carbons of the fatty acid, the stearic acid, we're actually generating 120 ATP. So based on this, we can do a calculation to show how much ATP we're getting per carbon. And if you do this, then you see that the lipid is actually 33% more efficient at generating the energy from that fuel. You can also think about it as storing energy, because before you do this process, it's energy stored. So basically the lipid is 33% better at giving energy through these processes than the carbohydrate. So you can say, based on this, that the lipid is a more efficient fuel than carbs. And this is because you get more ATP per carbon of fatty acid than glucose. Okay, so you probably heard before that fats are more energy efficient than carbohydrates, and this is why. So we can see that the fatty acids are able to produce significantly more ATP than the glucose. So there's a calculation there showing that per mole we're getting 2.5 more times more mole than from the same amount of glucose. So we can have a look at this calculation in a little bit more detail. So if you start with 1 molecule of stearic acid giving 120 ATP, using that same ratio tells us that 1 mole of stearic acid will produce 120 moles of ATP. So basically you're getting 120 times more than you're putting in. So you're putting in 1 mole of stearic acid, getting 120 moles out. So 1 mole of stearic acid, if you add up the molar mass using the periodic table, you get 284 grams per mole. So that means we need 284 grams of stearic acid to produce 120 moles of ATP. So for 1 gram of stearic acid, you're actually getting 0.423 mole per ATP. If we do the same thing for glycerol, 1 mole of glycerol produces 30 moles of ATP, and the molar mass for glucose is 180. So if you do 180 grams of glucose and dividing that by 30 moles of ATP, then for 1 gram of glucose, you're actually getting 1.67 moles of ATP per gram. So you can see that per gram, you're getting about 2.5 times more mole of ATP for the fatty acid than you do for the glucose. So this is just showing in a bit more detail why it's actually more energy efficient to use our fatty acids as the fuel rather than glucose.